Okay, we're here at day 11, day before our first test, so we need to finish up what I would consider to be the review material, Chapter 1, 1.7. We kind of came to a stopping place where we have the only topic yet to talk about is the cycloid, and I mentioned that term yesterday, and I could, trying to read your expressions, could tell that that was not something that was deeply rooted in your mathematical background. It's a pretty interesting math problem. So let's begin today talking about the cycloid. Actually, let's not do that. I have a pending question. So let's answer that question, or try to answer that question. Actually, I think we have a couple of pending questions. Page 73. This is from section 1.6. And the first question from the other day was 18. And I made some suggestions, kind of a jump start on problem 18, but we didn't actually see it through. So let's do that. And the other one is 28. Is that correct? A couple of you asked about 28. All right, 18. The function, kind of an ugly function, 3 plus x squared is pretty tame. But then we've got tangent of pi x over 2. And then it asks a couple questions about this function related to some inverse questions. It says, what is the f inverse of 3? So what we probably, here's what I think the authors are trying to get us to do with this problem. Get us to think about, under the function, what can we take the f of and get 3? That way, when we switch that around and take the f inverse of 3, then we're going to basically get this number. Is that right? And do I think they intend for us to find the inverse and then actually, I don't think that that's the case. I don't think it would be bad if it were just 3 plus x squared, but that extra tangent of pi x over 2, I think that is a good sign to me anyway that they expect us to do this problem a different way. So how do they expect us to do it? Well, just take a look at the function and see if you can think of an x value. And I know you can think of a couple of simple x values that you could plug in there. I know of a real simple one that I would try first. I'd try 0 to see if when I plug in 0, it actually gives me 3. That'd be my first attempt. And if that didn't work, I'd probably try 1. And if that didn't work, I'd try -1. I'd try a couple of what I call obvious values. But if you'll put 0 into this function, 3 plus 0 squared, well, that's 0. I like that because I want my answer to be 3, right? So I like 0 squared because that doesn't change 3 by much. And then the last part, tangent of pi 0 divided by 2. Well, that's tangent of 0. And what's the tangent of 0? 0. Thankfully, it's also 0. So we get 3 plus 0 squared plus the tangent of 0. So I think, and to give this a name, just by inspection, kind of trial, a simple trial and error here, trial without error because we lucked out and our first trial worked. The f of 0 is 3. Therefore, the f inverse of 3 is got to be 0, right? Just interchange x and y. So that's the first part. The second part, I think they're trying to get you to compose a function with its inverse and be back with the element that you started with. So the f of the f inverse of 5 is 5. Okay, and I don't think there's any tricks there why it would not be 5. Is that okay? Does that suffice for 18? So this was an assigned problem, right, on the stuff that I just collected. Did you get that? Did you get f of 0 equals 3 and then just flop those around? No? Yes, some of you did? Okay, probably more of you didn't than did, but when it gets real ugly like that, and a function, when you would try to interchange x and y and it's really a mess, that's probably not the direction. The direction is probably to take a look at it and try some simple values and see if any of them work. All right, 28 is the other one, also from 1.6. What page is this on? Same page, page 73. 28, the directions, find a formula for the inverse. So what are we given? I'll go ahead and write it y equals, I think it's handed to us at, well, it is y, that's good, 1 plus e to the x over 1 minus e to the x. So I know a couple of you had this problem, gave you some grief. How about the rest of you? Is this problem one that we should be spending our time looking at?
Yeah.
Yes. How many of you feel like you did this one correctly?
Took me a while though.
Took you a while? Well, if you feel like you had some success with this, what did you do?
Interchange x and y.
Okay, interchange x and y. So now we're moving to a new function. It's no longer the same function, it's a completely different set of points. X equals 1 plus e to the y. I have a pretty good idea what happens here, what I think is going to happen. And now we want to solve this for y. So let's somehow try to consolidate all the y terms, everything that has a y in it. We want to get all those terms together. So how can we begin that process?
Take the natural log.
Eventually, I think we want to do
Cross
that.
multiply.
X by 1 minus.
Okay, so I like both those suggestions. Let's take this one first, cross multiply or multiply both sides by the denominator. So in essence, x is x over 1, so let's cross multiply x times that, and then 1 times that one. And go ahead and distribute. And then what I described, let's try to get everything that has a y in it on one side and everything that doesn't have a y on the other side. So let's send all the y terms this direction. So I'd have to subtract 1 from both sides and what? Add x e to the y. So if we do that, what are we left with over here? That's gone. That's gone. Looks like e to the y plus, I think this can be done. I think this is going to work out fairly nicely. And then over here, what do we have? X minus 1? Okay. Since we have an e to the y in both terms, we know we're eventually going to try to isolate the term that has y in it. So let's see if we can only get one term to have y in it. It's in there once, and it's in there x. And one more step will isolate the term that has y in it. Is that right? 1 plus x. Okay, and I think we're ready for suggestion number 2. Take the natural log of both sides, since we've got y in the exponent position and we want to get y out of that position. So here's what we have. X minus 1 over 1 plus x equals e to the y, natural log of both sides. That's kind of a waste of space there, but just to clarify what it is that we're doing, the natural log of e to the y, that's a self-answering question. What power do you raise e to get e to the y? Is y. So I think you could end with that. Call that, if the original function is f, then this would be f inverse. Now, some of you may have gone a step further with this. You have some of you said, no, you did not go a step further. What is the natural log of a quotient? The difference of the natural logs, right? So you could, you don't have to, you could write the answer like that, right? That's equivalent to the natural log of the quotient, but that's just a matter of preference. Either one of these, if you get to that point in the problem, then I know you know what you're doing. Is that a fair test question, you think?
It's a real good test.
It's a looking better every second, right, as we go. I think that's a fair test question, I'll be honest with you. That, to me, and I know that there's a little bit of a tricky step there, is that you end up with an e to the y, and you would much rather have y by itself, but I think that's a worthy question at this point in the game, that if you have an e to the y, that you know how to get that y out of that exponent position by taking the natural log of both sides. So I think that's a fair test question. Yes, sir.
Did you already collect these?
Yes. I'll just get
Turn
you
it
at
off
the
class?
end of class. Yeah, you can go ahead and change this one if you didn't get it, but no, not really.
You know how you took the natural log of both sides? Could you just change it from exponential form to logarithmic form instead? I mean, is it the same thing?
It ends up
Mm-hmm. That's right.
So does it matter?
Doesn't matter.
Okay.
So at this stage of the problem, she's suggesting to just change that to logarithmic form. So log to the base e of that quotient is y. Okay? That's fine. Taking the natural log of both sides accomplishes the same thing. Yeah, in fact, this is, you don't need to write this. The natural log of e to any power is in effect that power. That's why we're doing it, is to get that variable up there in the exponent position isolated. Anything else with this, or anything else with another problem? Yes.
In general, for 21 and I think 57, when you have a scientific word problem, or why is it that you can't just switch the variables like you do for anything else? I mean, I know theoretically why not, but
21, and what was the other problem?
57. And if,
57.
like for 57, if I switch the n and the t, just like we do with the x and the y, it doesn't work.
It should, to find the inverse. All right, let's just try the linear version, the problem 21. So here's a Celsius Fahrenheit equation. I think we actually developed this, didn't we, in here?
Yeah.
One day. Just trying to do a linear example. F is greater than or equal to negative 459. Okay, express the Celsius temperature C as a function of the Fahrenheit temperature F. So we want to, that expresses C in terms of F. Find a formula for the inverse and interpret it. What is the domain of the inverse function? Okay, well, if we're going to find the inverse, new function, let's just see what happens here. Let me reread this, make sure I'm doing this right. Find a formula for the inverse function and interpret it. Okay, what is the domain of the inverse function? Okay, now are we, probably a good thing I reread it. Is this function that was given to us the same function as this one?
No.
No, we're completely flip-flopping the x's and y's or c's and f's, right? Now, could we take the original function and solve it for f? Okay, we could, right? And then we'd have basically the same relationship, the same exact set of points, where we could plug in certain c values and find the corresponding f value, right? But now we're abandoning that. We're going to go to another function, which is the inverse function. So if we do that, we interchange the roles of c and f and we solve for c, right? We would typically interchange x and y and solve for y. We're going to interchange c and f and solve for c. Multiply both sides by, what, 9/5? So we have 9/5 f equals c minus 32. And add 32. Whoops, plus 32. So that is a complete role reversal, right, of C and F. Now, of what value is that? That's the next question.
Well, I think that's what I got originally, but the answer in both the solutions book is exactly the first thing that you said, where you just solve for f. So that's what I understand theoretically why you can't do that, why you can't just make it a completely different equation, because then it'd be different points.
Well, if that's the case, then what they gave you for an answer in the back of number 21 is not the inverse.
Okay,
It's
and
a
that's the same thing with
restatement.
57.
Okay.
So that's what really confused
Okay.
me.
57, I can see upon reading Part B, when will the population reach 50,000, that it seems to me like they're asking you really to use the same, your same function, except you're going to solve for the other variable. Yeah, so truly that's not an inverse, right?
Yeah, because this is a find the inverse of this function.
Yeah.
So, but then it gives.
Okay, that's a good clarification then. I'm glad you asked those, because we just found the inverse,
Yeah.
right?
Yeah.
Where we have a new set of points that is exactly the original set flip-flop. Okay? So I don't think that's really what they want you to do. They want you to solve the original equation for the other variable. To
So
me,
if you ask for an inverse on the test, you
right,
want us to
I want
actually
you
flip-flop.
to interchange x and y and solve for y, or interchange c and f and solve for f. Yeah, that's good that you brought that up. Anything else from that problem set? Okay, well, let's finish 1.7 and then talk about the test briefly today as well. So the thing that we lack from finishing Chapter 1 and finishing Section 1.7 is that of a cycloid. And I found a little wording difficulty actually in the way the authors have described a cycloid, so it's interesting to see that it's kind of a semantics problem on those two problems, 21 and 57 as well. Here's what they say, and I think there's a term misused here. It says the curve traced out by a point P on the circumference of a circle in the coordinate plane as the circle rolls along a straight line. Along the circumference of a circle. I think our wording can be a little better. Isn't the circumference a number, right? That is found by taking pi times the diameter or twice pi times the radius. So I don't really think they want to say along the circumference, just any point on the circle itself, right? That's not the circumference of a circle, that's the circle itself. So we want to take a point on the circle itself and then roll it along a straight line, and as you do that, it traces out a set of points. So here's what they want. Here's how we form a cycloid. Okay, and this is one of the best little diagrams you'll ever see. Not really, but hopefully it'll work. So here's the dot, the point that's not on the circumference of the circle, but it's on the circle itself. The circle is just this set of points, right, around the outside. So we set that dot at location 0. Now just pay attention to the dot itself. As we roll the circle along, notice the path of the dot. And then when we roll it once all the way around, then it's right back down at location 0. Is that okay with everybody? Now, if you have your book open to page 79, you'll see then what this looks like in a cyclic fashion, is that this point kind of comes up and then reaches its peak right here, right? And as we continue to roll this thing, then it rolls all the way back down. And if we continue to roll it beyond that, it starts that cycle all over again. So that's how you actually form a cycloid. So it's not along the circumference of the circle, it's just a point on the circle itself, and then you roll it in a straight line and it traces out this thing called a cycloid. Okay? You probably know me well enough at this point in time in this semester to know that I'm going to spend a few seconds on where these equations come from. So this is a diagram from your book, copied. But I want us to, rather than just take the equations, the parametric equations that are handed to us, I want us to see where they come from on the diagram. So this point, point P, is the point on the circle that I just did the little demo, and we start it right here. We start it at point 0. And then as we start to roll the circle along the straight line, you can see the cycloid itself being formed. Okay? This path right here is what happens to that point P as we roll the circle along that straight line. So that's the cycloid itself. Now what we want is some way to figure out what is the x value of that point in terms of distances on this diagram, and what is the y value of that point. So here's point P, and we just kind of stop it, freeze it at some point in time. And we want to know the x value and the y value of that point P. So they draw this little diagram. This is over x and up y. So that's what we want to know, those two distances. How far over is it, x, and how far up is it, y. Now look at what the authors have given us here. We really want to know x. Isn't x the distance from O to T minus the distance from P to Q? Look at the diagram. Look at O to T, and then find PQ. If we have OT and subtract out PQ, that's what we want, right, for x? Mm-hmm. That's x. Now, what is O to T? Well, think about this little guy rolling along here. The line that it rolls along, isn't that a piece of the circumference? Right? So isn't O to T exactly the same as arc PT? O to T is exactly the same distance as arc PT, because we just rolled out the arc along the line, along the table here. So what is arc PT? Hopefully this rings a bell, and this is why I wanted to do this today, is that we could get a little review. This is supposed to be review. This is a new topic, I think, for most of you, but there is some review embedded within it. Isn't the length of an arc, you might remember this, S is arc length, isn't it R times theta? Does that look familiar? If the R is the radius and theta is the central angle in radians. Now look at this diagram. Isn't theta the central angle in this picture? So if you know the central angle and you know the radius of a circle, you can find the arc length. So that's this piece. OT is the same thing as PT, arc PT, and arc PT is r times theta. Theta's in radians. Okay, the other piece of this is PQ. What is PQ? Look at that right triangle in the middle of the circle. Look at PCQ. If I took this angle, theta, so I'm looking at that right triangle in the middle here, what's the sine of theta? Isn't it opposite over hypotenuse? Right? By the way, I've noticed when we start talking about trig in here, I've been teaching long enough to read people's faces. You're not liking trig as much as, I mean, not that you're really liking everything else, but I can tell that when we start talking about trig, some of you are not real comfortable about it. Now, does that mean that I'm going to take it easy on you and not ask much trig? No, it doesn't. It means that I'm going to make mention of the fact that I can tell many of you are uncomfortable with trig, and I'm going to make a recommendation that you look in the appendix in the back of the book and any other review materials that you have on trigonometry and get going with it. But I'm not going to let up on the trig because trig is all throughout this text. So if you're uncomfortable with it, I think it's up to you to make yourself a little more comfortable with it. So let's look at this little right triangle right here. Sine of theta is opposite PQ over hypotenuse, what, r? So can we take that little equation, that little trigonometric equation, that you're not going to give me that look anymore. I know that you're going to look at that like you feel confident with it now. Can you solve that for PQ? Cross multiply, right? PQ times 1 is what? R sine theta? And isn't that what that says right there? PQ is R times the sine of theta. So if you take r theta minus r times the sine of theta, and you factor out an r, that's the parametric equation that describes what x is. So it's got a little bit of an arc length in it, a little bit of a right triangle trigonometric ratio in it, and that's the end result. So that's x described in terms of theta. We want to know what y is, similar fashion. So is y TC, this whole distance, minus QC. Does that look good to you? If you took TC and subtracted out QC, would that give you our y value? I think that's it. What is TC? Well, that's easy. What's TC?
Radius.
That's just a radius. TC is a radius of this circle. And what is QC? Well, look at this triangle again. What's the cosine of theta? Cosine would be adjacent over hypotenuse. That'd be QC over R. So what is QC? R cosine? There it is. That's QC, R cosine theta. And again, even simpler, a radius of a circle minus basically a trigonometric ratio type statement, and factor out an r, and you end up with the parametric equation for y. So we have x in terms of theta. Now what is theta? Theta is the angle that's created, the central angle, by rolling this along, right? That's what theta is. And y in terms of theta. Okay, everybody reasonably comfortable with that? You're not going to have to prove this yourself at this point in time. Prove it to me that you can start with the diagram and come up with the parametric equations, but I want them to make it believable. Okay, so we have these two. Let's do a little bit with this. I'm going to need some calculator help here too as we go. So there's our two parametric equations for this cycloid. So we could make a table, which I think we ought to generate a few points. So let's start off with theta equals 0, and we're forced to use theta equals some angle in radians. And in fact, if you're ever in doubt in a calculus or a calculus-based class, never use degrees, always use radians. Radians is kind of a unitless description of rotation. If you say pi over 2, you don't need to say pi over 2 radians. It's understood to be radians. If you say 3, it's understood to be 3 radians. But if you want 3 degrees, you have to actually specify 3 degrees. If you don't see any unit at all, it's radians. So 0 radians. All right, let's figure out what the x value is. And let's say, well, let's just have it in terms of r. Let's say that the radius of this circle is r. That way we'll make our set of points in terms of r. So this would be 0 minus the sine of 0. 0 minus the sine of 0 is 0, right? So 0 times r is 0. Was that our initial x value? As you look at the picture you see on page 79, is that the initial x value? Yeah, what's the initial y value? It's also 0, because we're starting that designated point at 0, 0, and then we're starting to roll it. So let's make sure 1 minus the cosine of 0. Cosine of 0 is 1, so 1 minus 1 is 0. Let's go to pi over 2. Pi over 2, that's pi over 2, I'm going to need some calculator help here, minus the sine of pi over 2. I'll tell you what, let's make this a little bit easier here as we go. Let's say that the radius of our circle is 1. That way we don't have to have our answer in terms of r each time. So I know pi divided by 2 is about 1.57. Does that sound right? Right, the number pi divided by 2. And then I'm going to subtract out the sine of pi over 2, which is 1. So what's that, about 0.57? Okay, let's throw pi over 2 into the other parametric equation. 1 minus the cosine of pi over 2. What's the cosine of pi over 2? 0. I like that. Quick and confident now. So that's 1 minus 0, which is 1. 1 times the radius is 1. So as we roll through pi over 2 radians for our central angle, then we ought to be plotting the point 0.57, comma 1. If theta is pi, we've rolled through pi radians. That's pi minus the sine of pi. Sine of pi is 0, right? So pi minus 0 is pi. Pi times 1 is pi. So I'll get a decimal equivalent here, approximation. And the y value, 1 minus the cosine of, in this case, pi. Cosine of pi, think about where that is. Look, picture a cosine graph, and now we're at pi. Negative 1. 1 minus negative 1 is 2. So there'd be twice the radius, which is 2. Now here we are with our little friend here. We roll through pi. Is this where we are? Right here? We've rolled through a central angle of pi. Is that the peak? That point going to be at its peak? Let's see what happens. Three pi over 2. 3 pi over 2, let's see, that'd be pi plus another half pi. 3.14 plus 1.57, what, 4.71 roughly? Check me on that. I'm not an arithmetician by any means. So that's 3 pi over 2, 4.71, minus the sine of 3 pi over 2. What's the sine of 3 pi over 2? Negative 1. So we've got 4.71 plus 1, right? 5.71. And what's the y value? What's the cosine of 3 pi over 2? 0. 1 minus 0 is 1. Start to cycle back down, right? It's reached its peak in terms of the height, the y value, and now it's on its way back down. And take it through one complete roll around. 2 pi. 2 pi is 6.28 approximately. What's the sine of 2 pi? 0. So that's 2 pi minus 0, which is 2 pi times 1. And we need to check a value. I'm not liking a value that we see here, that I see. And let's put 2 pi in here. What's the cosine of 2 pi? 1. 1 minus 1 is 0. 0 times that is back to 0. So that seems logical. We've rolled through a central angle of 2 pi where that black dot is back down on the table. How about 3 pi over 2?
It's 4.71. Yeah, right. Oh. Yeah, plus 1.
3 pi over 2 is 4.71, right? And then we are subtracting the sine of 3 pi over 2, negative 1.
You're adding 1.
So 5.71. Is that all right? It doesn't look right to me for some reason. So if we plot these points in terms of the xy coordinate plane, so we've developed it in terms of two parametric equations. So we've got 0, 0. We've got 0.57, which is pi divided by 2, 1. Okay, all right. I think I just justified that. Why I didn't like it, I think it's okay now. So if we graph them, let's say this is 2 pi, so that would be pi. Which means that pi over 2 is here. And what's our largest value, 2? So 1 would be there. 0, 0. 0.57, that's pi over 2 is 1.57, so 0.57 is about right here. It's at 1. 3.14, or pi, we're up 2. Does that look like what that cycloid was looking like in your textbook? 5.71, this is 4.71 plus another little bit. Means we're here at 1. And then 6.28 or 2 pi, we're back down here. And then the thing starts all over again, right? There's one little loop, one piece of this cycloid. So we'll visit this problem. Will we visit it at the end of this course? Probably the beginning of the next course, 241. You can use some calculus methods to find the area under this curve. But it's nice to know what the curve is and what it looks like before we advance to another problem, the area under a curve. Here's some problems that I'd like for you to look at from this section. Page, sorry. And again, I'm hoping that everything is, for the most part, review, with the exception of this cycloid. Now, I can't remember if I picked a problem related to the cycloid or not.
Is cycloid gonna be in our test tomorrow?
No. No, I did not. I intentionally did not pick a problem related to cycloids. But I think it's valuable to take a first look at it, which I think is a first look for many of you, what a cycloid is. Okay, the test covers all of Chapter 1, so 1.1. Up to and including 1.7. Now, when I say there, let me clarify what we said about nothing at all with a cycloid. I think it would be a reasonable question for me to give you the parametric equations for a cycloid, not necessarily call it that, just call it two parametric equations, and have you plot some points, just like what we did. I don't think that would be unfair. But for me to ask you at this point in time to remember the equations of a cycloid or how to develop the equations, I don't think that would be a fair question. But to plot some points, that's a possibility, just as a generic parametric set of parametric equations.
You give us what x and y equaled, and we just had to plug in?
Yes.
All right.
Yeah, you could plug in through, theta equals 0, pi over 4, pi over 2, whatever. Enough points that you can sketch it. Any of you check out your graphing calculators to see how it would handle parametric equations? Anybody make an attempt yet? Be a good thing. It might save you some time to plug those into your calculator. The other thing is the appendix. And I believe that was Appendix B, circles and lines. And parabolas. Ellipses. And hyperbolas. And that's the content of the test. And I think I mentioned yesterday that we would approach it, that you would not necessarily be quoting me definitions, but that you would be able to take a problem that I would hand you about a parabola or a parametric equation and answer a question or a couple of questions about it. Find the inverse. Graph the original function and the inverse on the same coordinate plane. Find the vertex of a parabola.
We can use a calculator.
Yes, yeah. Calculators that are legal for the course, yes.
So for like studying and stuff, should we just go over the exercises that you've been giving us for homework?
I think that would be fair. Any example that we did in class. And certainly any problem that somebody had a question about that we actually did from start to finish up here. I mean, those would clearly be fair. I will look at the chapter review myself to see if I might find any good questions there in the chapter review. So whether or not you look at the chapter review is up to you. But I know if my teacher just said that, I would probably look at the chapter review. Now, normally we will spend an entire class period, or 40 minutes of a class period reviewing for a test, but as I stated earlier, this is review material, so we're getting a little bit redundant with the reviewing the review material. So test tomorrow. Okay, if you want to start 5 minutes early, we can do that, and then I'll give you 5 additional minutes at the end. And that concludes day 11.